At the bottom of the Jezero crater on Mars, a river once flowed. We know this not because someone was there to watch it. We know it because the river left its delta in the rock, a fan-shaped deposit of sediment laid down where a river slows and drops its load as it enters standing water. The Perseverance rover, which landed in Jezero in February 2021, has been traversing this delta for years, sampling sediment deposited by that ancient river. Jezero is not unique. Mars Global Surveyor's laser altimeter, mapping the entire planet's topography in precise detail between 1997 and 2006, revealed a landscape carved by water, valley networks branching across the ancient southern highlands like a river system photographed from altitude. Channels cut by what appears to have been moving liquid at scales comparable to terrestrial rivers. Basins whose flat, smooth floors are consistent with lake sediments. And in the north, a lowland region, the Vastitas Borealis, covering nearly a third of the planet, sitting several kilometers below the elevation of the southern highlands, with a geometry consistent with an ocean basin. Mars had water. The evidence for this is not theoretical. It is in the landscape, in the minerals, in the sediment layers, in the delta deposits that no process other than flowing water produces. The clay minerals detected from orbit by the Omega and Crism spectrometers on Mars Express and Mars Reconnaissance Orbiter require sustained liquid water to form, not a brief contact with moisture, but prolonged interaction between water and rock. Curiosity discovered in the floor of Gale Crater minerals including smectite clays and sulfates that form only in neutral pH water suitable for chemistry compatible with life. The question is not whether Mars had water. The question is where it went, and what removed it, and why a planet that appears to have sustained liquid water for potentially hundreds of millions of years, possibly over 1 billion years during its early history, is now a frozen desert with an atmosphere 100 times thinner than Earth's. The answer involves one of the most specific and least discussed features of Mars's geological history: the death of its global magnetic field. A planetary defense system that protected Mars' atmosphere from the Sun for perhaps its first several 100 million years, and then stopped. And in the silence left by its absence, the Sun quietly dismantled the ocean. If this is the kind of briefing you want more of, hit subscribe and stay with me. The mission begins now. Open the ancient Mars file. The Mars we can reconstruct from the geological record is a planet dramatically different from the one that exists today. The ancient southern highlands of Mars, the oldest terrain on the planet dating to roughly 4 billion years ago, carry the signature of a wet world. Their surfaces show valley networks that could only have formed through sustained liquid water flow. Their mineral compositions include clay minerals that require prolonged water-rock interaction. Their impact craters contain materials consistent with lake sediments. The Noachian period, Mars's earliest geological epoch, spanning roughly from 4.1 to 3.7 billion years ago, is when the water evidence is most concentrated. Valley networks, most of which date to this period, cut across the highlands in patterns that mirror terrestrial drainage systems, main trunk channels fed by tributaries, at branching ratios consistent with precipitation-driven runoff rather than the groundwater sapping that once served as an alternative explanation. The networks require not just water, but a sustained water cycle, something similar to rainfall or snowmelt feeding rivers over extended geological periods, not an isolated geological event. The Curiosity rover, which landed in Gale Crater in August 2012, provided the first direct, on-the-ground confirmation of the conditions Mars's water had created. Gale Crater was selected as the landing site specifically because orbital data showed the presence of minerals requiring water to form. Curiosity drilled into the lake sediments on the crater floor and found clay minerals, smectites, that form when silicate rock and water interact at neutral to slightly alkaline pH at temperatures consistent with liquid water rather than hydrothermal alteration. It found sulfate minerals and early-stage carbonate minerals. It found in the chemical composition of the sediment all the elements required by Earth life: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, plus a range of chemical energy sources including both oxidized and reduced forms of iron and sulfur that organisms could exploit for energy. The Curiosity findings were specific in their characterization. Gale Crater contained an ancient lake with habitable conditions, not merely the physical presence of water, but the chemistry that Earth life requires. Whether life existed there is not established. That the conditions for life as we know it were present is confirmed by direct measurement. The Perseverance rover, landing in Jezero Crater in February 2021, extended this on-the-ground picture to a different type of ancient water environment. Jezero was selected because Jezero Crater's ancient river delta, the fan-shaped sediment deposit visible from orbit, provided a geologically richer target than Gale's ancient lake floor. Perseverance has been sampling the delta material, finding organic molecules preserved in the ancient sediments, and collecting sample tubes for eventual return to Earth by a future mission. The delta is not ambiguous in what it represents. A river carried material into this crater. It deposited that material as it entered standing water, and the record of that river and that lake is preserved in the sediment for a rover to read billions of years later. The collective picture from orbiting spacecraft and surface rovers is of a Mars that was during its Noachian period, a world with lakes, rivers, precipitation, and potentially a northern ocean in the lowlands. A planet where water was cycling through the surface environment in something resembling an active hydrological system, not identical to Earth, not continuously warm and wet throughout its history, but genuinely, measurably, prolongedly wet. And then something changed. Pull up the faint young sun paradox file. Early Mars's water history carries within it a specific and long-standing puzzle that complicates simple narratives about when and why Mars was wet. The sun was less luminous in the early solar system than it is today. Solar physics constrains this. As a star converts hydrogen to helium in its core, its luminosity increases over time. The young sun, approximately 4 billion years ago, was emitting approximately 70% of its current energy output. At Mars's orbital distance, about 1.5 times Earth's distance from the Sun, the solar energy reaching Mars in the Noachian would have been substantially less than Mars receives today. This creates an apparent contradiction. Mars today, receiving its current solar energy input, maintains a surface temperature averaging approximately negative 60 degrees Celsius, far too cold for liquid water. But Mars today has a very thin atmosphere. The earliest Mars had more solar energy available than Mars today, but also not nearly as much as modern Earth. For early Mars to have had liquid water at its surface, it would have needed a greenhouse effect substantial enough to keep temperatures above water's freezing point, powered by an atmosphere thick enough to provide it. What that early thick atmosphere contained, and how it maintained surface temperatures warm enough for liquid water under a sun that was less luminous than today's, is the so-called faint young sun paradox as applied to Mars. Carbon dioxide is the obvious candidate greenhouse gas. Mars currently has a CO2-dominated atmosphere, and a denser CO2 atmosphere in the past would provide more warming. But detailed climate models show that CO2 alone, even at concentrations several times current atmospheric levels, may not be sufficient to warm early Mars to above freezing without additional greenhouse warming from other gases such as methane or hydrogen, or from other warming mechanisms such as impact-delivered heat. The resolution of this paradox is not fully established in the literature. Some models suggest that early Mars had periods of warming driven by large volcanic eruptions or major impacts that briefly created liquid water conditions, interspersed with cold periods. Others suggest that a combination of greenhouse gases, including some hydrogen, produced by volcanic outgassing, could have provided sufficient warming for sustained liquid water. The geological record shows sustained water activity, not brief episodic events, which argues for sustained warmth over extended periods. But the specific atmospheric conditions that produced that warmth remain under active research and genuine uncertainty. This uncertainty is relevant to the main question of what killed Mars's ocean, because the mechanism of death depends on what the atmosphere looked like when it was alive. In 1997, the Mars Global Surveyor spacecraft entered Mars orbit and, among its other science objectives, began measuring the Martian magnetic field with a sensitive magnetometer. The expectation was that Mars, like Earth, would have a global magnetic field generated by an active planetary dynamo, a fluid motion of conducting material in the core, driven by the planet's rotation and internal heat, producing a dipole field extending into space and deflecting the solar wind. The magnetometer found something different and scientifically significant. There is no current global magnetic field on Mars. The planet has no dynamo operating today. Where Earth's magnetic field extends tens of thousands of kilometers into space and deflects the solar wind, Mars's global magnetic environment is absent. The solar wind impacts Mars's upper atmosphere directly with no magnetopause to deflect it. What Mars Global Surveyor's magnetometer did find was remnant magnetism, a record of ancient magnetic fields preserved in the rocks themselves. In the ancient southern highlands of Mars, the oldest terrain on the planet, the crust is strongly magnetized in alternating bands. The specific pattern, alternating zones of opposite magnetic polarity, similar in character to the magnetic striping found on Earth's ocean floors, where seafloor spreading has recorded reversals of Earth's magnetic field, indicates that these rocks solidified and cooled within the presence of an ancient magnetic field, locking in a record of that field's direction and intensity at the time. The intensity of the remnant magnetism in Mars's ancient southern crust is remarkable. In some regions, it is stronger than the most intense remnant magnetism found in Earth rocks, suggesting that Mars's early dynamo generated a field at least as strong as Earth's current field, possibly stronger. This was an energetically active planetary interior. The younger terrains on Mars tell a different story. The volcanic provinces of Tharsis and Elysium, large volcanic systems whose surface ages are estimated as younger than the ancient southern highlands, show almost no remnant magnetism. This absence is the key diagnostic. When Tharsis's lavas erupted and cooled, There was no global magnetic field present to magnetize them. The magnetism that exists in the ancient southern crust had been acquired by those rocks when the dynamo was active. By the time Tharsis erupted, beginning in the late Noachian and continuing through the Hesperian, the dynamo had stopped. Correlating the geological ages of Mars's terrains with their magnetic properties establishes a timeline. The dynamo appears to have been active through the period when the southern highlands solidified and to have ceased before the younger volcanic provinces formed. The estimated time of dynamo cessation, based on the ages of the terrains involved, is approximately 4 billion years ago, near the end of the Noachian period when Mars's water evidence is most concentrated. The coincidence between the end of the dynamo and the beginning of Mars's long drying trend is not coincidental. The magnetic field and the ocean appear to have been coupled. The field's operation was part of what maintained the conditions for the ocean, and the field's cessation began the process by which the ocean was lost. Read the magnetic field discovery file. In 1997, the Mars Global Surveyor spacecraft entered Mars orbit and, among its other science objectives, began measuring the Martian magnetic field with a sensitive magnetometer. The expectation was that Mars, like Earth, would have a global magnetic field generated by an active planetary dynamo, a fluid motion of conducting material in the core driven by the planet's rotation and internal heat, producing a dipole field extending into space. The magnetometer found something different and scientifically significant. There is no current global magnetic field on Mars. The planet has no dynamo operating today. Where Earth's magnetic field extends tens of thousands of kilometers into space and deflects the solar wind, Mars's global magnetic environment is simply absent. What the magnetometer did find was remnant magnetism, a record of ancient magnetic fields preserved in the rocks themselves. In the ancient southern highlands of Mars, the oldest terrain on the planet, the crust is strongly magnetized in alternating bands reminiscent of the magnetic striping found on Earth's ocean floors. This specific pattern indicates that these rocks solidified and cooled within the presence of an ancient magnetic field, locking in a record of that field's direction and intensity at the time. The younger terrains on Mars tell a different story. The volcanic provinces of Tharsis and Elysium, large volcanic systems whose surface ages are estimated as younger than the ancient southern highlands, show almost no remnant magnetism. This absence is the key diagnostic. When Tharsis's lavas erupted and cooled, there was no global magnetic field present to magnetize them. The magnetism that exists in the ancient southern crust had been acquired by those rocks when the dynamo was active. By the time Tharsis erupted, the dynamo had stopped. Correlating the geological ages of Mars's terrains with their magnetic properties establishes a timeline. The dynamo appears to have been active through the period when the southern highlands solidified, and to have ceased before the younger volcanic provinces formed. The estimated time of dynamo cessation, based on the ages of the terrains involved, is approximately 4 billion years ago, near the end of the Noachian period, the same period when Mars's water evidence is concentrated. The coincidence is not coincidental. The magnetic field and the water appear to have departed together on a geological timescale for related reasons. Open the later Mars file. After the Noachian, after the valley networks stopped forming and the ancient lake systems began to dry, Mars was not immediately transformed into the dead desert it is today. The Hesperian period, which followed the Noachian, lasted roughly from 3.7 to 3 billion years ago and is characterized by a specific and dramatic type of geological activity that left its own distinctive record. The massive outflow channels of Mars, Kasei Vallis, Aris Vallis, Mangala Vallis, and dozens of others date primarily to this later period. These are not river systems in the sense of the Noachian valley networks. They are the scars of catastrophic flooding, channels up to hundreds of kilometers wide and thousands of kilometers long. Carved not by sustained precipitation and river flow, but by sudden, enormous releases of water from pressurized subsurface reservoirs. The volume of water implied by the geometry of these channels in individual flooding events dwarfs any flood in recorded human history. Some events may have released water at rates comparable to the combined flow of all Earth's rivers simultaneously, sustained for perhaps weeks to months before subsiding. What appears to have happened during the Hesperian is a Mars where the surface was no longer warm enough for stable liquid water, the greenhouse atmosphere had been thinned, and temperatures had dropped, but enormous reserves of water ice permafrost still existed in the subsurface, along with possibly some liquid water under pressure at depth. When these subsurface reservoirs were suddenly depressurized by volcanic intrusions, by large impacts that penetrated the permafrost, or by the collapse of the overlying frozen crust, they released catastrophically to the surface, carving the outflow channels before refreezing and evaporating. The water from these Hesperian floods did not persist. Mars's surface conditions by this period were not warm enough to maintain liquid water long-term. The floods filled low-lying areas briefly, possibly creating temporary shallow seas in the northern lowlands before the water froze, evaporated, and was lost to space or incorporated into permafrost. The Hesperian outflow channels are the record of Mars's water in retreat. Massive final expressions of water reserves built up during the wet Noachian being suddenly released into an environment that could no longer sustain them. Aris Vallis is the channel where Mars Pathfinder landed in July 1997, the first successful Mars lander since Viking. The landing site was chosen because the channel had been carved by flooding and the resulting surface was strewn with rocks of diverse origins, transported from distant locations by the ancient flood, providing a sampling of a wide range of Martian geology in a single accessible location. The rover Sojourner, which accompanied Pathfinder, analyzed the composition of rocks deposited by a flood that had occurred more than 2 billion years before it arrived. Opened the Tharsis file. Any account of what happened to Mars's atmosphere and water must address the largest volcano complex in the solar system, which sits on Mars's surface like a continent of its own. Tharsis is a dome of volcanic rock, approximately 5,000 kilometers across and 10 kilometers high, centered near Mars's equator and occupying roughly 1/4 of the Martian surface area in terms of its influence on the planet's shape and gravity. Olympus Mons, the solar system's largest known volcano, at approximately 22 kilometers tall and 600 kilometers in diameter, sits at the edge of the Tharsis region. The entire structure represents an enormous quantity of volcanic material erupted over billions of years, though most intensively in the early and middle history of Mars. The formation of Tharsis is relevant to Mars's atmospheric and ocean history in two directions, pulling opposite ways. On one hand, the volcanic eruptions that built Tharsis released enormous quantities of gases into Mars's atmosphere over billions of years, primarily carbon dioxide, water vapor, and sulfur dioxide. The CO2 and water vapor are both greenhouse gases, and their volcanic addition to the atmosphere during Tharsis' most active period may have contributed to whatever greenhouse warming maintained early Mars's liquid water. In this reading, volcanic outgassing was part of what kept Mars warm. On the other hand, the formation of Tharsis caused Mars to undergo true polar wander, a reorientation of the entire planet relative to its rotation axis, driven by the mass imbalance of adding a continental-scale volcanic province to one hemisphere. The poles shifted by approximately 20 degrees from their pre-Tharsis positions, redistributing where ice could accumulate and how Mars's climate zones were arranged. The sulfur dioxide released by Tharsis' volcanoes presents a specific climate complication. While CO2 is a warming greenhouse gas, SO2 reacts with water vapor to form sulfuric acid aerosols, which are highly reflective and cool the climate by blocking sunlight. If Tharsis' volcanic activity was dominated by SO2 producing eruptions during certain periods, the climate effect could have been cooling rather than warming, contributing to the transition from a wet to a dry Mars rather than helping maintain the wet period. The net climate effect of Tharsis on early Mars is therefore not a simple story of either volcanic warming kept Mars wet or volcanic cooling killed the ocean. It involves competing effects operating on different timescales, with the balance between them depending on specific eruption compositions and rates that are difficult to reconstruct from the geological record alone. What is not ambiguous about Tharsis is its scale. The largest volcano in the solar system is on Mars, a planet that is now geologically dormant by most measures. The discrepancy between Mars's ancient volcanic productivity and its current inactivity is itself a consequence of the same cooling process that killed the magnetic dynamo, a smaller planet cooling faster, its interior heat gradually declining below the threshold needed to sustain mantle volcanism as well as the magnetic dynamo. Open the magnetic shield file. To understand what the magnetic field's absence meant for Mars's water, it is necessary to understand what the magnetic field was doing while it existed. Earth is continuously bombarded by the solar wind, a stream of charged particles, primarily protons and electrons, flowing outward from the Sun at approximately 400 to 800 kilometers per second. This particle stream carries enough energy to ionize atmospheric molecules and, without any protective mechanism, would strip away Earth's atmosphere over geological time. Precisely the fate that has happened to Mars. What protects Earth's atmosphere is the magnetosphere, the region of space dominated by Earth's magnetic field. The magnetosphere deflects the solar wind around Earth, forcing it to flow around the planet rather than directly impacting the atmosphere. The boundary where the solar wind meets the magnetosphere, called the magnetopause, is typically located approximately 10 Earth radii away from the planet's center. This creates a protective bubble within which Earth's atmosphere is largely shielded from direct solar wind exposure. Without a global magnetic field, Mars has no magnetopause to deflect the solar wind. The solar wind interacts directly with Mars's upper atmosphere. This interaction strips atmospheric particles through several mechanisms: direct impact by solar wind particles that knock atmospheric molecules into escape trajectories, heating of the upper atmosphere that allows gas to reach escape velocity, and a process called photoionization, in which solar ultraviolet radiation ionizes atmospheric molecules, which are then swept away by the solar wind's electric and magnetic fields. The loss of atmospheric material through these processes is ongoing on Mars today and has been directly measured by the MAVEN spacecraft. The Mars Atmosphere and Volatile Evolution Mission, MAVEN, launched in November 2013 and arrived at Mars in September 2014, carrying instruments specifically designed to measure how Mars's atmosphere is currently being lost to space. Its findings, published in a suite of papers in Science and Nature in September 2015, provided the first direct measurements of Mars's ongoing atmospheric loss and the first direct evidence that the solar wind is stripping Mars's atmosphere today. MAVEN carries several instruments relevant to measuring escape: the Solar Wind Ion Analyzer for measuring solar wind properties, the Suprathermal and Thermal Ion Composition Instrument for measuring escaping ions, and a Neutral Gas and Ion Mass Spectrometer for composition. Together, these instruments can measure both the properties of the solar wind arriving at Mars and the composition and energy of the particles escaping from the Martian atmosphere. MAVEN measured current atmospheric escape at approximately 100 grams per second on average, about 3 kilograms per minute, or roughly 4.5 metric tons per day of atmosphere being lost to space, even under current solar conditions. This rate might seem small, but multiplied over millions and billions of years, it represents an enormous total mass loss. More significantly, MAVEN's key observational finding was what happens during solar storm events. When the sun produces a coronal mass ejection, a burst of energetic plasma that reaches Mars and temporarily increases the energy and particle flux impacting the Martian atmosphere, the escape rate increases dramatically. MAVEN measured increases of 10 to 25 times the average escape rate during these events. In the early solar system, when the young sun was far more active than today, events comparable to modern solar storms were essentially the sun's constant baseline output. A young sun with today's storm conditions as its everyday state would have stripped Mars's atmosphere at a rate potentially 10 to 25 times faster than modern MAVEN measurements, and under early solar conditions, possibly faster still. The MAVEN data allowed scientists to reconstruct a rough atmospheric history, working backward from the current escape rate and scaling for solar activity history. The models suggest that Mars has lost the equivalent of an atmosphere with a surface pressure of perhaps 0.5 to 1 bar or more to space over its history, potentially enough to have sustained a significant greenhouse effect in the Noaken if that pressure was present then. The uncertainty is large because both the early solar activity and the early atmospheric thickness are incompletely constrained. But the direction is clear: Mars has lost a very substantial fraction of whatever early atmosphere it had, primarily to solar wind stripping in the absence of a magnetic field. MAVEN also measured the DH ratio, the ratio of deuterium to hydrogen, in Mars's current water. This ratio is approximately 5 times higher than in Earth's ocean water, indicating that Mars has preferentially lost the lighter hydrogen isotope to space over geological time, leaving the heavier deuterium behind. This enrichment in deuterium is a direct chemical fingerprint of hydrogen loss. And hydrogen is what you get when water molecules are broken apart by solar radiation in the upper atmosphere. with the resulting hydrogen atoms escaping to space. The DH ratio independently confirms that Mars has lost a substantial amount of water, specifically through atmospheric escape, over its history. Scan the What Remains file. Why did Mars's magnetic dynamo stop while Earth's continues to operate? The answer lies in the comparative sizes of the two planets and how size determines the rate at which a planet cools. Mars has a mass approximately 1/10 of Earth's. A smaller planet has a smaller volume relative to its surface area. It has proportionally more surface through which to radiate heat to space, and proportionally less interior volume generating and containing heat. Smaller planets cool faster. The Moon, at approximately 1.2% of Earth's mass, appears to have solidified its interior and lost any geological activity billions of years ago. Mars, at approximately 10% of Earth's mass, falls between the Moon and Earth on this spectrum. A planetary magnetic dynamo requires a specific condition to operate. Fluid electrically conducting material in the outer core must be in convective motion. On Earth, the outer core is liquid iron nickel, kept fluid by heat from the crystallizing solid inner core. The temperature gradient between the hot inner core and the cooler mantle drives convective circulation in the liquid outer core. Earth's rotation gives this circulation a helical character that generates and sustains the magnetic field. As long as the outer core remains liquid and the temperature gradient drives convection, the dynamo operates. The InSight lander, which landed in November 2018 and operated until December 2022, provided the first direct seismic measurements of Mars's interior structure. Using Marsquakes, seismic events generated by volcanic activity, meteorite impacts, or internal stress, InSight's seismometer built up a picture of Mars's interior by measuring how seismic waves travel through different layers. The results were published in several papers in Science in 2021 and 2022. InSight revealed that Mars has a relatively large liquid outer core of iron alloy mixed with lighter elements, primarily sulfur, and possibly oxygen and hydrogen. The core radius is approximately 8,800 kilometers, larger relative to the planet than expected from pre-InSight models. This surprisingly large, light element-rich liquid core has implications for the dynamo's cessation. A core with more light elements would have a lower melting temperature and might have different convective behavior than a more iron-rich core like Earth's. What InSight's seismic data could not directly reveal is the heat flow from Mars's core to its mantle, the critical parameter that determines whether convective circulation in the core is sustained. InSight carried a heat probe that was designed to measure heat flow from Mars's interior, but it was unable to penetrate to the required depth, limiting this critical measurement. The heat flow question, which would directly constrain how long the Martian core's convective circulation could have been maintained, remains constrained only by theoretical models rather than direct measurement. The theoretical models suggest that Mars's smaller size and resulting faster cooling rate caused the convective circulation in the core, and with it, the magnetic dynamo, to weaken and eventually stop approximately 4 billion years ago. The specific mechanism proposed involves the mantle's increasing thermal resistance as it cooled. As Mars's mantle cooled and solidified further, its ability to conduct heat away from the core decreased. This reduced heat flux from the core to the mantle may have reduced the temperature gradient driving core convection, below the threshold needed to sustain the organized circulation that generates a magnetic field, even while the core itself remained liquid. The cessation of the dynamo exposed Mars's atmosphere to direct solar wind bombardment, setting in motion the slow, billion-year process of atmospheric loss that eventually removed the greenhouse warming, keeping surface temperatures above water's freezing point, and with it, the conditions for Mars's ocean to exist. Open the What Remains file. Where did Mars's water go? Some of it is still on Mars. The polar ice caps contain water ice. Confirmed by multiple measurements, including radar sounding from the Mars Reconnaissance Orbiter's SHARAD instrument that has mapped ice layers extending kilometers beneath the surface at both poles. The volume of water ice in the poles, if melted, would cover the entire Martian surface to a depth of roughly 5 to 35 meters, depending on the estimate. A substantial amount of water, but a fraction of what an early ocean containing a few hundred meters of water equivalent would have required. The regolith, the loose surface material, is thought to contain additional water ice in permafrost form across much of the planet, particularly at mid-latitudes and higher. Radar measurements and neutron spectrometry from orbit have mapped hydrogen-rich material beneath the surface consistent with water ice at various depths. MAVEN's measurements of hydrogen escaping from Mars's upper atmosphere provide an additional line of accounting: the ratio of deuterium to hydrogen in Mars's current water, measured by ground-based and spacecraft observations, is approximately 5 times higher than in Earth's ocean water. This enrichment in the heavier isotope of hydrogen results from preferential loss of the lighter isotope to space. When water molecules are dissociated by solar radiation and hydrogen escapes to space, the lighter hydrogen one escapes more readily than the heavier deuterium. The enrichment ratio observed in Mars's current water implies that Mars has lost the equivalent of a global ocean layer several meters to tens of meters deep to space in the form of escaped hydrogen. Mineral sinks represent a third reservoir. Clay minerals, sulfate minerals, and carbonate minerals found in Mars's ancient terrains all contain water chemically bound into their crystal structures. The formation of these minerals extracted water from the early Martian hydrosphere and locked it into solid rock, where it remains today. The extent of this mineral sink is difficult to quantify from orbital observations, but it represents a geologically permanent removal of water from the active hydrological system. The distribution suggests that Mars's early water was partitioned across 3 fates: escape to space, freezing at the poles and in permafrost, and chemical incorporation into surface minerals. The ocean didn't evaporate in the literal sense of the word. It was dismantled over hundreds of millions of years by a combination of atmospheric escape, freezing as temperatures drop, and geological incorporation into minerals. Close the mission briefing, pull out the final report. The question this investigation addresses: what specifically caused Mars's ocean to end, and what does that mechanism tell us about the relationship between planetary magnetic fields and habitability? Here is what the evidence confirms. Mars had liquid water at its surface during the Noachian period and into at least parts of the Hesperian period, extending from approximately 4 billion to perhaps 3 billion years ago. The evidence is in the valley networks, the lake sediments, the delta deposits, the clay minerals requiring prolonged water contact, and the topographic consistency of the northern lowlands with an ancient ocean basin. The duration and character of Mars's wet period is subject to ongoing research, with different models proposing different scenarios. A persistent ocean, a series of episodic wet periods or something between, but the water's existence is not in serious scientific doubt. Mars had a global magnetic field early in its history, confirmed by the remnant magnetism detected by Mars Global Surveyor in the ancient southern crust. This field ceased to operate approximately 4 billion years ago, established by the pattern of which Martian terrains are magnetized and which are not. MAVEN has directly measured ongoing atmospheric loss at Mars, establishing that the solar wind is currently stripping Mars's atmosphere at a measurable rate even under the Sun's current relatively mild conditions, under the far more intense solar conditions of the early solar system. This loss would have been substantially faster. The cessation of the magnetic field, which previously deflected the solar wind, allowed this stripping to begin. The smaller mass of Mars relative to Earth caused its core to cool faster, reducing and eventually ending the convective circulation in the core that generated the magnetic dynamo. This is the root cause underlying the chain of events leading from active Mars to dead Mars. Here is what the evidence leaves genuinely uncertain. The specific climate conditions that sustained liquid water on early Mars under a young, dimmer sun are not fully established. Models suggest thick CO2 atmospheres with potential contributions from other gases. But the precise combination and the specific climate states involved remain under active research. The timeline of the ocean's decline, exactly when the transition from wet to dry became permanent, is constrained within broad ranges, but not precisely. Whether Mars ever had life during its wet period is not established. The conditions Curiosity found in Gale Crater, neutral pH water, chemical energy available, all the necessary elements, are consistent with habitability for the types of life we know from Earth. Whether life actually arose, and whether it persists in any form today in subsurface environments, are questions that no current Mars mission has answered. Here is where the honest parallel to Earth resides, stated with the precision the evidence supports. The mechanism that killed Mars's ocean, core cooling, magnetic field loss, solar wind stripping of the atmosphere, applies to any rocky planet of any size in any star system. The rate at which it operates depends critically on the planet's size and the composition and activity of its core. Mars, at 1/10 Earth's mass, reached the threshold of dynamo failure billions of years ago. Earth, at its larger mass, maintains an active liquid outer core and a functioning dynamo today. Earth's magnetic field will not last forever. The outer core is slowly losing heat to the mantle. The inner core is growing as the outer core crystallizes. Eventually, on timescales of billions of years, not millions, the conditions that sustain the convective circulation driving Earth's dynamo will change. The specific future of Earth's magnetic field on these timescales is genuinely uncertain in its details. Earth's core chemistry and heat flow may sustain the dynamo long after Mars is stopped, or may not. The analogy to Mars is structural, not a prediction of a specific Earth timeline. What Mars tells us, with the specificity that comes from having an example to study rather than just a model to evaluate, is that the loss of a magnetic field, if it occurs, removes the primary protection against solar wind stripping of an atmosphere. The atmosphere can be lost on timescales of hundreds of millions to a billion years if the solar wind has direct access to it. The ocean, dependent on the atmosphere for the greenhouse warming that keeps surface temperatures above freezing, then cannot be maintained. The sequence from active dynamo to dead world is not instantaneous, but it is irreversible. Mars has not recovered from its dynamo's shutdown in 4 billion years. The water is still there, in ice and minerals and traces of atmosphere. The geology of the ocean is still written in the southern highlands and the delta in Jezero crater, but the ocean itself and the conditions that made it possible have been gone for approximately 4 billion years. The most direct cause was the loss of a magnetic field that was, by any measure, the most important thing keeping Mars habitable. The mission brief ends here. Perseverance is still driving through the Jezero Delta, sampling rock that a river deposited when Mars had an ocean. The remnant magnetism in the southern crust still records the direction of a dynamo that ran for a few 100 million years and then stopped. The MAVEN spacecraft is still measuring the atmosphere leaving the planet at 100 grams per second. The timeline between early wet Mars and present frozen Mars is roughly 4 billion years. What happened during those 4 billion years is mostly what happens when a planet's core cools, its magnetic field goes quiet, and a star is left with unobstructed access to an ocean that had nowhere to go.